All right, so in this video, we're going to continue our discussion with linear differential equations by studying a common application. These are called mixture problems. And so the setup is actually very mechanical, as is solving the actual linear differential equation. Getting there is equally as mechanical. So we're going to let y of t be the amount of salt in the tank at time t. So the differential equation dy dt is going to be very intuitively a rate in minus a rate out type problem. The rate in, we're going to break apart into concentration inflow multiplied by inflow rate minus our rate out, which is concentration outflow multiplied by outflow rate. Okay, so we're going to have essentially four different things that we need to fill out from the problem. Now, I went ahead and I've included here this a problem that we're going to work. If you guys are going to pause the video and take a minute and read it, you can. Otherwise, I'm just going to kind of jump right in. Now, I'm going to first start by getting set up what I need. So my dy dt is going to be those four things that I mentioned. Now, most of this information is going to come straight from the problem. We've got concentration inflow. So brine containing 1 pound of salt per gallon enters. So 1 pound per gallon. So 1 pound per 1 gallon enters the tank at 2 gallons per minute. So our inflow rate is going to be 2 gallons per 1 minute. So 2 gallons per 1 minute. Now, for the outflow, the concentration outflow, I'm going to come back to here in a second. The outflow rate is generally given to us as well in these problems. And you can see it leaves the tank at 3 gallons per minute. So 3 gallons per 1 minute. Okay, so now the concentration outflow. For the concentration outflow, we're going to need to use part of this as what it is we're actually studying. So our top part here is going to be y of t, the amount of salt in the tank at time t, and then used as a ratio, we'll now need to consider how much substance is actually in the tank at time t. And so what I'd recommend on a problem like this is just drawing a picture. If this is our tank right here, we're coming in at a rate of 2, we're leaving at a rate of 3. So you can see that this tank would be losing overall substance over time. It would be losing it by a unit of -1. So if we start at 60 gallons, which is what it says, we start at 60 gallons, then we're going to be -1 per unit of time. That's where this -1 comes into play. If this would have been a +5, it would have been 60 plus 5 times t. T again is for time. But because we're losing liquid, it's going to be that -1 times t. Okay? So, fortunately, all of these setups are essentially the same. You're always going to get a lot of information straight from the problem. Generally speaking, I put my y of t right here, followed by this part, which is the part that we actually have to think about a little bit. But because we start with 60 gallons and we're losing 1 unit per unit of time, we've got this -1t right here. Now, I'm going to clean this up a little bit. I'm going to call this a dy dt equals a 2 minus 3 over 60 minus t times y. And I'm also going to put in the initial condition. The initial condition is the y of something equals something. Well, the tank initially contains 60 gallons of pure water. And if you remember, we defined this y of t as the amount of salt in the tank at time t. So at time 0, we have 0 salt in the tank at time 0. So this is a general setup now for our word problem. It is going to be a linear differential equation, as I pointed out. And so to solve this, we're going to go ahead and need to make sure it's formatted correctly. So I'm going to go ahead and move this up a little bit more here. And to do so, I want this to look like a dy dt plus a 3 over 60 minus t y equals a 2. This would give us then the ability to use the integrating factor of e raised to the 3 over 60 minus t dt. Now, when you work this out, this is actually just going to be e to the negative 3 times the natural log absolute value 60 minus t. Again, that's one of those where if you let u equal the bottom, then you're going to get that natural log coming out of there. And so if you need to work that on the side, feel free to. And then to clean this up a little bit, I would have considered taking this 3 up top here, and then the e and the natural log will do away with one another again, leaving us with just 60 minus t to the negative third. All right, so we'll take that integrating factor now, and we're going to multiply both sides. We've got a 60 minus t, t to the negative third. It's a minus there. And when I do this, right now it's just going to be distributing. So we've got a 60 minus t to the negative third, dy dt. And then we'll have a plus 3 times 60 minus t to the negative second times y equals a 2 times 60 minus t to that negative third. All right, so this big mess right here, remember this is just a product rule, and so it is a product rule for y times our integrating factor of 60 minus t to the negative third. In the last two examples I've walked through with you, I would encourage you to maybe take a minute and convince yourself that when you find this derivative using the product rule, you do in fact end up with this. And then the right-hand side I'm just going to leave alone. So 60 minus t to the negative third. All right, so we are ready to integrate. The left-hand side, again, I'll continue to move this up. I really want to keep that word problem on our page so I can refer back to it here in a little bit. So if I go ahead and start integrating then, the left side will be the y times 60 minus t to the negative third. The right-hand side will be a 60 minus t to the negative second plus c. Again, that's also going to be a u sub for this thing, and you'll be able to go ahead and then simply add 1 and divide all the way through. And so once we have that now, I'll go ahead and I'll solve for y. So our y is going to be a 60 minus t plus a c times 60 minus t cubed. All right, so I went ahead and divided this off. So when I divided it off, it left me with a positive 1 here, and then I divided it here and flipped it around to get a positive number. All right, so this is our general solution. Because we have an initial condition right here, the y of 0 equals 0, I'm going to go ahead and plug that back in. So y of 0 equals, that's going to be a 60 plus c times 60 cubed, which is just kind of an ugly number. And then solving for c, I'm going to get a negative 1 over 3600. So our y of t is going to be 60 minus t minus a 60 minus t cubed over a 3600. So that's our particular solution for the differential equation. Now, if you think about what this is the solution to part A here. Find the amount of salt in the tank after t minutes. If we know that the y of t here is defined as the amount of salt in the tank after t minutes, then when we come down here, this is the function, or the formula, if you will, that'll give you the amount of salt in the tank at time t. If you want to know how much salt is in the tank after 5 minutes, plug a 5 in and it'll tell you. Okay, so that's part A to this problem. Part B is actually something that you guys are going to solve in a quiz. And so when you see the quiz and I refer back to the mixture problem from the video, this is the problem that I'm talking about. Part B, what is the maximum amount of salt ever in the tank? That's one of those that I'm going to leave up to you guys. So we've done the hard part. We've gone through the new material when it comes to these mixture problems, and they're all very much the same way, very mechanical in nature. And then even the solving process, like we pointed out before, using the integrating factor, is very mechanical.